Say hi.
Hello! I'm Mr. Willis. Section Chapter 2, 2.3. Is it too dark? Can you see in there? Can you see me?
I can't really see your face. You just kind of have one. You kind of have a shadow face.
Yeah. If you're ever watching these after the recording, you can't really see me very well, but you can see.
Well, then it's useless.
But that's the important stuff up there, Coach, isn't it?
This is a little more important. If you do need to see me, I'll turn the lights on, so then that you can see me. Okay, water. We're talking about water today. What is this? It's Mr. Thornton.
Right there, you're moving that mouse, and there's apparently some sensor that's sensing that you're moving it.
Yep.
What are you moving it in relation to?
There's a little laser that shines on the floor.
Whoa.
That is how the floor is moved.
That's top notch.
See?
You need to just log off.
I know. I gotta log back on. It's me. Mr. Thornton forgot to log off.
I just videotaped your password, Coach.
You can't tell from the tape what the password is.
I videotaped your key motions. I'm going to go back in slow motion and check it out.
Yeah? Interesting. Tell me when you figure it out.
And then after we do that, we can
I'll
change
change
our
it.
rates on the computer.
Why would you want to change them from all hundreds, though?
Because that seems like we cheated if we get all 100.
Gotcha. Good thinking. Okay.
I'll run 2, 3 now.
Water, yes. Today we're talking about water. Actually, I'm going to start on page 26, which discusses hydrogen bonding, and we'll need to do that.
I think we're all up to date on hydrogen bonding. We did that for like 3 chapters last year.
Well, good. So this should just be reviewed.
For hydrogen bonding. The exact test was like.
We didn't really know anything about hydrogen bonding. We just knew like hydrogen bonding.
It's circle. It's the answer to everything.
Alright, here we go.
Hello. Computers can do that? Alrighty then.
Okay. Oh, there we go. Yeah. Okay. Last time we had class, we talked about the water molecule. Well, we didn't. We talked about the bonding that goes on in the water molecule. They're called covalent bonds. Do you remember covalent bonds?
Yeah.
Mad, what type of bonds are covalent bonds? What do they do?
They share electrons.
Shared electrons, that's right, very nice. And here it shows the electron model with a hydrogen. Now remember, hydrogen only has 1 electron. But if you look at this picture, it looks like it has 2. The reason why is because it's sharing with this oxygen. Oxygen actually has 6 in its outer level, but in order for it to be happy, it needs 8. So the hydrogen brings in 1 and shares with this oxygen, and another hydrogen brings in 1 and shares with this oxygen. So the oxygen ends up with 8 electrons, and so it's happy. And each hydrogen ends up with 2 electrons, and so it's happy because it has a full first level. 2 in the first is a full level. And that was how covalent bonds work. Do y'all remember that? Covalent bonds are quite exciting, aren't they?
Yeah.
Okay. Now here's the deal with water is, though, and this is what makes water an incredible substance. It shares the electrons unevenly. It doesn't evenly share. The hydrogens and oxygens are attracted to, have a different attraction to the shared electron pair. In this case, the oxygen kind of hogs those electrons. It pulls those shared electrons closer to itself. It's kind of greedy, that oxygen is. It pulls those electrons real close to itself. And the hydrogen, the poor little hydrogen over here, it doesn't have, the electrons are very far away from it. So we say it's unequal sharing. Do y'all remember this from chemistry? And it causes it to be what's called polar. Polar means charged. If you look at this model over here, the oxygen there has a slightly negative charge. That little symbol means partial charge, and there it is right there. It's very fun to draw that symbol. You do it again, just because I enjoy it so. It's fun, isn't it?
The camera didn't catch that, Coach. One more time.
After a while, it's probably too dark to see.
I got it.
But if you draw that symbol, that means partial charge, and that's partial positive, and that's partial negative. But what that means is that the water molecule, since the oxygen is kind of hogging those electrons, and the reason for that is the oxygen has a whole lot of protons in its nucleus. It's got 8 protons in its nucleus, so it kind of has more of a pull on the electrons than the hydrogen does that only has 1 proton. And so the electrons hang out near the oxygen, and it makes it partially negative, and the hydrogens thus are partially positive because those electrons are so far away from it, they don't have as much negative charge. So the net effect is the water molecule's like a little magnet. It's got a partial negative there and partial positive there. And if you put a bunch of water molecules together in the same place, you form hydrogen bonds. And like y'all said, hydrogen bond, that's the answer to everything, right? Well, the little dot, the dotted lines that you see here are called hydrogen bonds. They are attractions between the negative end of one molecule and the positive end of another molecule. And it kind of holds them together. It holds water together. See, if I get some water on my finger, it stays in a little drop. Do you see how the drop, did y'all see that there? That was so fun. Look.
Hold on.
Look at the water is kind of, do we need the light on for this? For full camera effect?
I need to zoom in on it too.
Okay, full camera effect here. If I get some water, notice how together, the water likes to stay together. It stays in a little drop. Do you see? It stays together. All those little water molecules are attracted to one another. Let's pour it on a desk. And if you notice, look, it all stays together. It doesn't like spread out in all directions.
And it's got the little like, what's it called? Surface tension.
Yeah, we'll talk about surface tension in a minute. Look how it flows together.
Hit it. Hit
It's
it.
going, it's going.
Come on now.
Let's give it a little more.
Boost. Oh, here it goes.
Ah, see?
Oh, it's going again.
Now wait till the next person in the next class comes and sits down. Well, so that's one thing hydrogen bonds do. Hydrogen bonds cause water to stay, what we call that property, cohesiveness, to stick to one another. And that's why water forms droplets. When water is falling from the rain, it forms a round drop because all the water molecules are kind of suctioned into one another. So there's a whole bunch of properties of water molecules because of these hydrogen bonds. Now, one of the properties is it's hard to change the temperature of water. Temperature of water doesn't change easily. It's hard to make water hot, and it's hard to cool water down. Have you ever tried to boil water? You put the water in a little pan, and you sit there and wait, and you're waiting, and it's just hard. It takes a long time. Or how about raising the temperature of your swimming pool? You know, if the temperature changes and all of a sudden it's been cold because it's winter, and then one day it's hot, and you go, yay, it's hot, let's go swimming. Well, the pool's not going to be warm for another month or two.
I wouldn't say a month, Coach.
Less than a month?
A lot less than a month.
Couple of weeks?
I mean, I was thinking like maybe
your pool's obviously smaller than mine.
I guess so. Yes,
But do you have 2 summers of
Olympic
pool
size
experience?
What?
Do you have 2 consecutive summers of pool experience?
3.
I don't know what you mean.
18.
Lifeguard.
3.
Oh, you mean working at a pool?
Cleaning pools between summers and staring at pools.
I don't work at the pool. I lie down by.
Apparently, you're not as adept in pool knowledge.
Okay, maybe not. But I'm just saying.
He is good
Water.
water
So
knowledge.
you go when it's warm. It suddenly gets warm. The pool's going to take a long time to change. But at the same time, if it suddenly gets cold, like at night, the air gets cold, and you're like, ooh, it's cold. But you jump in the pool and it feels real warm. Have you ever noticed that? Water doesn't like to change temperature very much. And so we say that the way to say that scientifically is water has a high heat capacity. Heat capacity means how much heat it can hold. And this is good for living creatures because it helps keep your body temperatures stable. The human body is maybe 80% water. It depends on the person. Females have more water than males. But anyway, there's a lot of water in your body, and that keeps your temperature, it helps keep your temperature constant. And constant temperature is good for organisms. It can get cold outside, but the body stays the same, so you don't have to make a lot of adjustments. So we say that water has a high heat capacity. Here's another thing. Water has a high, what we call heat of vaporization. You ever heard of that before? Heat of vaporization? What is it from chemistry? Some of y'all chemistry pros.
Which something, yeah.
Goes into a gas.
How much heat it takes to go from liquid to gas. And you can see water, just 1 gram of water, which isn't very much, takes 540 calories to go from its liquid state to its gaseous state. And which is a lot. Do y'all know how to read graphs, by the way? You're going to have to read a lot of graphs in AP biology. You have to kind of look at this graph and look at the 2 axes.
It's quite simple.
And understand that as temperature goes up, as you go from left to right on this graph, temperature is going up. And the calories of heat energy that the water has is going up. So yeah, it's not too bad, but you're going to get used to seeing graphs because you'll be graph experts by the end of the year, hopefully. Now, so the fact that water has a high heat of vaporization is because of the hydrogen bonds. To go from liquid to gas, the hydrogen bonds have to be broken. The little water molecules have to break off the surface here and fly out into the air. They have to pull away from the other water molecules, and that takes a lot of energy. And so we use this, organisms that are warm-blooded use this for cooling. If you put some water on your skin, some water on my skin, my hand feels kind of cool. It's on my face. Oh, wait, that's not water, that's acid! Joke, it's water. The reason why that feels cool is because what happens is when water evaporates into the air, it's going from a liquid to a gas, right? And it's taking heat with it. As it goes from a liquid to a gas, it pulls the heat from your body, and it pulls a lot of heat. It pulls 540 calories per gram of water of heat from your body, and that will cool you off. And so that's the purpose of sweating, is so that the water will evaporate and take heat with it. And that's what the elephant's doing here. It's saying, gosh, I'm hot, spray some water, it'll evaporate, that'll cool me off, and plus I get this lady off my back who's riding. Okay. Water is a good solvent. That's another property that comes with hydrogen bonding. The lights again so you can see. Here I have some sodium chloride.
Indeed.
What's the formula for sodium chloride?
NaCl.
NaCl, very good. And what I'm going to do is I'm going to get some of it in this water, and it's going to dissolve. So I'm going to take my spatula here.
That's a spatula?
It's called a spatula here. It's not. It doesn't look like a cooking spatula.
Yeah.
Does it?
Not
I
really.
don't know why they.
Maybe they're cousins.
I think these came before the cooking spatula.
Really?
Yeah, I think so. Anyway, notice this is a solid and this is a liquid, this water, and I'm going to drop it in there. And if I just stir it up a little bit, just like a magic trick, it's going to completely disappear.
You could increase the surface area too. That would help. Or agitate it. Or heat.
Yeah,
or
I'm doing it
you could
faster.
heat it.
Could heat it, that would make it go faster. Anytime you can get the molecules moving faster. But look, the salt is gone.
It's still there.
Ta-da!
You just can't see it.
It is still there, it is dissolved. And you wouldn't know if by looking the difference between this salt water and regular water. You could taste it and tell the difference. This would be kind of salty right now.
I would imagine so.
No.
Just a little salty though. I mean, you could probably dissolve all this salt in there.
I bet you couldn't.
I think you could.
I don't think you could.
Have you ever done an experiment where you've dissolved as much salt as you possibly could?
Just completely saturate the H2O.
Yeah, it's amazing.
I don't know.
It would be like, wow,
I think we
dissolved
should.
a lot of salt.
I've had like, I think 3 classes with you now. This is my
Yeah.
3rd class, and you've run into that podium twice.
I know. I've never had the podium before.
Oh, you haven't?
Yeah.
So it's new.
I'm getting used to it.
Oh, okay.
Like we
So,
said,
let's take a look at why this happens. Why does the salt dissolve? Well, if you remember, the sodium and the chlorine were ions. We called them ions because they were charged. And sodium is a charged particle, and chlorine is a charged particle, and all the waters are charged particles. They're polar. Polar means charged. So this water molecule being polar, the negative oxygens are attracted to the positive sodiums, and they literally will pull the sodium and chlorine apart from one another. Remember, the sodium and chlorine are present in the salt crystals in this kind of configuration, but what the little water molecules will go up to the sodium, and all the negative charges will surround the sodium, and the sodium will be more attracted to the water that's on the outside surrounding it than it is to the chlorines, and will come off. And the same thing happens to the chlorines. The chlorines are attracted to the hydrogens that are positively charged, and many water molecules will surround this thing and pull it off. And so one by one, the atoms in the salt crystal come off and spread out into the water. And it is dissolved.
Can I go to the bathroom, Coach?
Yes, who's going to run that for you? Just leave it running.
I'll just have it facing.
Very good.
Just don't do any crazy salt
See the
experiments.
screen? Okay.
I got you. Yeah.
So that's dissolving. Now, not everything dissolves in water. The only things that will dissolve in water are charged particles. Anything polar, anything charged will dissolve in water. But if I take some oil, here's ammonia, by the way. Ammonia is NH3. Ammonia will dissolve in water. Just spread out, and ammonia will seem to be gone. Let's say I take some vegetable oil. How about you get on the camera for this?
I bet you $100 it doesn't dissolve.
It's not going to dissolve. This is a non-polar molecule, and it's a very big molecule. And in 2 days, I'll show you the structure of an oil molecule, but it's really large, and it's not charged. If I pour some oil in here, it doesn't dissolve. Stir this baby up, just like we did the. No matter how much I stir it, all the little oil, it's not going to dissolve. It goes up to the top. It's lighter than the water, so it'll float up to the top.
This is a good zoom right here.
Yeah, it's a pretty good camera, isn't it? So I can't get that oil to dissolve. It'll stay like it is, That's cool when it goes down like that. I enjoy that part. It'll stay non-dissolved forever.
Perhaps you
You
should
leave
put
it
some
in
soap
there.
in it, Coach.
Soap would help break it up.
Mhm.
Soap is also a nonpolar molecule, and a nonpolar substance will dissolve in another nonpolar substance. But you put a polar, and a nonpolar together, and they won't dissolve. So that's kind of cool.
Do the little make it fall down and come back up thing again.
Like when I first pour it in.
Yeah, I missed that.
It's exhilarating when you do that.
Oh, that is cool.
So that shows that the oil is less dense.
The oil is less dense. That's why it floats.
Yes.
Yep. Have you ever seen froth on the ocean when you're walking by the ocean? That's just a bunch of oils and fats and stuff that came from creatures that live in the ocean.
So I shouldn't eat that.
You could eat it. There's a bunch of other stuff in there you probably don't want to eat.
Have you ever eaten it before?
Never.
Yeah.
I've never just eaten the froth. No. Okay. Hello. Now, another property of water, page 28, is that it's cohesive and adhesive. Two more words you have to know. What does cohesive mean? Do you know that one?
Teamwork.
Cohesive
It brings things together.
Means they stick together. They stick to one another. Water molecules stick to one another because of the magnetic nature. It's like a magnet. There's a positive end and a negative end, and those hydrogen bonds hold it together. That's why water forms droplets. Water is also adhesive. Adhesive means it likes to stick to other things. If you noticed when I put my finger in there, I'm not going to put my finger in there now with all the oil. But when I put my finger there earlier, the water stuck to my finger a little bit. And so water likes to stick to itself, and it likes to stick to other things. This makes water very good for transporting, for moving. The fact that it likes to stick to one another, if I were to take a drop of water and kind of drag it along the desk, I could kind of drag it along the desk with my finger. I need to do that, I think I need to do that.
We're going to need the lights for this.
Hold on, yeah, we're going to have to turn the lights on. Get some more water and go back along on the desk here. This back up here. And I'm going to pour some more water on the desk. Okay, now let's say I wanted that water, let's say I wanted to move the water. I could touch it to my finger and it's going to be adhesive to my finger. And I could kind of drag it along. And I could move a lot more than just what I'm touching with my finger, because the water adheres to my finger, and water molecules that are behind it adhere to those water molecules. So it's kind of like you're dragging kind of like a string of them. You know, it's kind of like a train or something. You can drag it along and other molecules will follow because they're all attracted. Does that make sense? And they move very easily, because if you could look at one individual water molecule, it would be kind of rolling around over other water molecules.
What's it do?
It's like rolling around like this. And they're kind of like a tumbling, you know, like a bunch of people just rolling around one another. I don't know when that would ever happen, but maybe in some kind of weird Cirque du Soleil thing. You know, if you've ever seen that, or like the Blue Man Group, or I don't know. A lot of Vegas shows have people doing things like that. So this helps in transport in like a tree. water is sucked in through the roots, and it has to go up little tiny tubes in the tree. And you would think that gravity would pull the water back down, but the little individual molecules cling to the sides of the tube, and other molecules below them are attracted to those molecules. So it keeps the water in a nice column that goes all the way up the tree to the leaves. So that's cohesion and adhesion are important for movement of stuff, movement of dissolved substances through organisms. Like your blood. Your blood's got a whole bunch of stuff dissolved in it. And your blood can move your food all the way from your stomach, where it's absorbed, all the way to all your other organs, like sugars, for instance. When you eat sugar, it gets into your blood, and your blood dissolves it and transports it from one place to another. Now, surface tension. Water has a high, what we call a high surface tension. All the molecules, since they're attracted to one another, they're always pulling inward. If we think about the surface of a lake, hold on, let me get my pen. Here's a bunch of water molecules. I'm just going to draw a few because it takes a long time to draw a lot.
I think I'd get the picture better if you drew several dozen.
Here's the surface of the water. The water molecules at the surface are all attracted to one another. They have attractions to one another, little hydrogen bonds. I should draw them as dots. But they're not attracted to anything in the air. They're only the general direction of attraction is downward. And so all the molecules at the surface are being pulled downward by all the other water molecules down here. And if everything's being pulled down and in, it makes the surface really tight. It's like pulling down on a rubber. Let's say you had like a rubber, like a trampoline, and you pulled down on it, the surface will become even tighter. And it's hard to break that surface, and there are insects and things that can walk on the water like that.
Have you ever tried to put soap in the water next to one of the floating insects?
Would it fall through?
Oh, it was awesome.
Yeah.
It was awesome, Coach.
What about that? Have y'all ever done that?
Yes, we did last year.
Balance a paperclip on the surface of the water? Let's hear what Pierce Brosnan, who played 007 for one or two movies, The Living Daylights was one of them. Let's hear what he has to say about surface tension of water.
Water is made up of many millions of molecules which are attracted towards one another. At the surface, the molecules are attracted more into the bulk of the liquid than to the air above, and that creates a tension at the surface layer. It's elastic, almost like a trampoline or the surface of a balloon. It's as if the molecules are always being pulled inwards. That's why water drops are round. The overall effect is that the drops are surrounded by an elastic skin. Walking on water is a talent possessed by members of the insect group. One of the first may have been the springtail. Springtails live in damp places, so they already have a high degree of water repellence, and they don't fall through the surface if they spring onto a pond by mistake. But some species of springtail live their lives almost entirely on the water's surface. It's the aquatic springtails that have mastered the art of walking on water. For them, the elastic surface is almost as solid as a floor. A full-grown springtail is not much larger than a pinhead. The little one is no bigger than a pinpoint. Yet both have managed to walk on water and exploit a new environment. But there are larger animals that have learned how to do this too. No, it's not frogs. The next type up is somewhat smaller, and you can find it near slowly moving water. It's a semi-aquatic bug called a water measurer. Those are its eyes and forelegs. It's called the water measurer because it looks like a ruler on legs. The body is waterproof like the springtails, but more interesting are the surfaces of its feet. Thousands of water-repellent waxy hairs cover the feet. At the end are claws in a sort of penknife arrangement. These aren't like the spikes of a springtail. They're for use on land. The measurer divides its time between the two habitats. Hairy legs poised on the water trampoline, the measurer is a true water walker.
Yeah, and then you put soap right in there, and then
they fall
they
through?
just fall.
And they die.
I guess.
That's sad.
It's exhilarating, Coach. You
Is
should
it?
try it.
When
Yeah.
did you do that?
I don't know. I just remember seeing like some stuff there, and I knew from my studies that soap breaks the surface tension.
Yeah, it does.
Mm-hmm.
Let's go. Next time I see that and I happen to have some soap out there by the lake.
Or if you're showering in the lake, then, I mean, do that thing with some soap.
We'll see. Okay, another property of water that is due to hydrogen bonding is that ice is actually less dense than liquid water. Ice is frozen water, solid water, is less dense than liquid water. Now, this isn't normal. This isn't something you usually run into. Normally, when things get colder, their molecules aren't moving as much. And the less molecular movement you have, the smaller a substance will be, like metal, for instance. As the colder it gets, the smaller a metal container will get. Maybe you've heard that to get a ring that's stuck, you could heat it, and it'll expand a bit. Have you ever heard about that? But that's not true with liquid water. Liquid water, when the molecules are hot, and well, are not necessarily hot, but when the temperature is high enough, the molecules are moving all around, and there's no real structure to it. And a drop of water, the molecules are just moving everywhere, and that's what you have. That's when you have water as a liquid. However, if you make it cold enough, the molecules quit moving so fast, and because of the hydrogen bonds, they take up a very rigid crystal arrangement that looks like a bunch of hexagons. And where we have all the dots you see are hydrogen bonds.
Except for the one on the left, the vertical one on the very bottom hexagon on the right side.
Here?
Up a little bit. Those two are two hydrogens connected to each other.
You're right, they screwed up.
Uh-oh.
Ooh. That
Yeah,
is just
it should be like that.
Should be.
I don't know why they did that.
And they're lazy.
Good. Should be a detective.
The top left too, they got some
Yeah,
mess
is it
up.
again?
It's all over the place. It's just it's a mess. It's a mess.
This hexagonal arrangement, though, leaves a bunch of empty spaces within an ice crystal. And you have this regular pattern and an empty space, and it causes ice to actually expand when it gets cold, which is unlike almost any other substance. If you take, let's say you're at one of your parties, I know how y'all's parties are, because I watch movies about high school parties.
Oh, Bible studies?
And if you take a beer, and you want to get it cold fast, and you put it in the freezer, and you forget about it, and it gets cold enough, the water in the beer bottle will expand and break the bottle.
What if you have a can?
It won't even break the can.
Hmm.
And that's all due to this property that water expands when it freezes. Now, how does that have any effect on living things? Well, they talk about it in the idea of a body of water like a lake or like the ocean in areas near, say, near the poles. What happens is the air above the lake is really cold, and it causes the water to freeze. Now, if, like every other substance, water molecules contracted when they freeze, then the ice would become more dense, and it would sink to the bottom. And the next bit of water would be exposed to the air, and it too would freeze and sink to the bottom. And the next bit would freeze and sink to the bottom, and eventually the ocean or lake, wherever it's cold, would be frozen solid and would kill all the living things in it. And this would be a very different world from what we have now. When the ice freezes, it floats because it's less dense than water and insulates everything below it, and you can still have animals down there living in the water. Do you see what I'm saying?
Not me.
Oh, and by the way, ice is at its most dense, or water is at its most dense at 4 degrees Celsius. Once you get, water will kind of, as you cool water, it will kind of contract until it'll get closer together until it reaches 4 degrees, and then it'll start expanding as the ice freezes, and the density drops way down, as you can see, as soon as the ice freezes completely. So that's kind of a magic number, 4 Celsius.
Or there, it's freezing at 1 degrees Celsius instead of 0.
I think that it's showing that in order to be liquid, it has to be above 0. And so they're trying to, yeah, it looks like 1. Definitely. Because 0, it's ice.
0.5.
A little bit above 0, then it's liquid. Did we see this one yet?
Yes.
I don't think we saw this.
Or it's in our book. I thought.
Water is surprising stuff. The most common of compounds, water can be found in nature as a solid, a liquid, or a gas. Sometimes all 3 phases exist at the same time. One of the surprises of water is that it expands when it freezes, making it less dense than liquid water. Consequently, icebergs float rather than sink. Although water has an unusually high boiling point, 100 degrees Celsius, water can be seen boiling up to the surface in some hot spots on Earth. The fact that water remains in the liquid state between 0 and 100 degrees Celsius makes life possible in such a wide range of environments.
All these properties of water contribute to life in so many different ways that we find it hard to imagine life without water. So something like SETI, have you heard of SETI, S-E-T-I? The search for extraterrestrial intelligence.
Whoa.
That's astronomers whose job is to hunt for little green men.
Oh, you're part of that?
I'm not, but I would like to be. They look for planets out there that are in areas where liquid water could exist. Are there any other planets around our solar system where liquid water exists? A lot of it?
No.
We actually think there are a couple. We think Europa, which is one of the moons of Jupiter, might have a liquid water ocean beneath its surface, because we know that the core of it is hot, and the whole thing's pretty much ice. So somewhere there must be water down there.
That makes sense.
And if there is water, perhaps there might be little fish swimming under.
Maybe little green men.
Or little green men just going, gosh, we're trapped. Now, so that's kind of interesting. Life is very dependent on water for all those different things. Now, the last section, page 30, talks about acids and bases. And hopefully you got to these in chemistry. Acids and bases are caused by amounts of either hydrogen ions or hydroxide ions. And if the number of hydrogen ions in a liquid are large, then the liquid is an acid. And if the number of hydroxide ions is great, then it's a base. And if the number of hydrogen ions and hydroxide ions are exactly equal to another, it's neutral. And so in a sample of just water, of regular water, you're going to have the same number of hydrogen ions and hydroxide ions. Because when the water molecule comes apart, it forms one hydrogen and one hydroxide. So there's the same amount of the two. And in a normal sample of water, like in this, there's some water coming apart and going back together. It happens very often. Water is a pretty strong molecule, but it can come apart. So here's the pH scale that you need to know. It goes from 0 to 14. Anything below 7 is acidic. Anything above 7 is basic. And you can see just some sample things. Hydrochloric acid is a very strong acid. You might have used that in the chemistry lab. Look, stomach acid has a pH of 1. Lemon juice, soda, beer. That's y'all's beer, huh? 3.5 or 4. Tomatoes, coffee even bread is acidic. Normal rainwater is slightly acidic. Acid rain is what we call it. Beer, urine. It's pretty gross. I don't know why they put urine up there. Can't think of anything else. Pure water and tears, neutral. Human blood. We got blood, urine, and tears. The guy who made this figure, he was upset. Now, egg white seawater is actually kind of basic. And baking soda, antacids. If you have too much acid in your stomach, you take an antacid, and it is basic, and that neutralizes the acidity.
Could you just eat baking soda? Would that just have the same effect?
That would work. Mm-hmm.
What about
actually,
sodium
antacids
hydroxide?
are calcium carbonate, which is baking soda. What's that?
What about sodium hydroxide? Could you just eat some of that and it would solve the acid problem in your stomach?
That would, yeah, but unfortunately, well, let me explain the nature of this table. Every one that you go up or down in pH is actually a 10 times difference. So this is what we call this a logarithmic scale. That means, for instance, human blood has 10 times the amount of OH minus ions as pure water. Baking soda has 100 times as much.
If pure water has
Great Salt Lake 1,000 times as much. So every step you go is an extra 0, which means if you try to drink some sodium hydroxide, it has about 10 million times as much OH minus ions as tears. So that might cause problems. Yeah.
Oh, if pure water has 0 OH ions in it, and seawater, say,
yeah,
human blood has 1,000 or 10,000 or whatever times as many, wouldn't it be also 0? Because 0 times 10,000 is 0. There's a flaw with your scale.
Well, actually no, and let me tell you why. Because pure water doesn't have 0 hydroxide ions. It does have some, because water breaks up very often, and you'll have some hydroxide ions over here and some hydrogen ions. It's just the same amount.
Okay.
They're balanced.
They're balanced, yeah. So actually, even a very strong acid like hydrochloric acid has some OH minus, but just not very much. Yeah. And each step up you go is an extra 10 times as many. That's called a logarithmic scale. This is an extra reading section on acid rain. You hear about acid rain. What happens is your tailpipe of your car is putting out a lot of chemicals that are light.
Or Hercules.
Float up in the air, or Hercules, or your air conditioner, or anything you run that uses electricity puts out some pollution at somewhere where they're making the electricity. And anyway, the molecules float up in the air, and hydrogen ions will come off of them, and it makes the air a little bit acidic. And so when the rain absorbs that hydrogen, those hydrogen ions, and when it rains down, the acid comes down. And with humans on the planet, all of the rain, every time it rains, it's acid rain. It's not, you hear about acid rain and you think, oh, it's acid raining there, but our rain's okay. No, all the rain everywhere on the planet is slightly acidic. In places with a lot of pollution, it's even more acidic. In some places it gets so acidic that it can kill entire forests. It'll eat up statues and stuff. It's never so acidic that when it hits your skin, it's like burning it, like in that movie Aliens. Remember when the alien is dripping? It's got acid for blood. No, did you not see that?
I think I missed it.
It's like
What about rain in like some crazy pollution place?
It gets pretty bad. The worst rain ever was pH 3 or 2.5, which if you look at the pH scale, it's like it's raining lemon juice.
Oh, that-
Thank you for recording. You can turn that off.